All right, everyone, thanks so much for attending. We are quite excited to have Nathan Kutz back in Cambridge. Nathan is the Robert Bolles and Yasuko Endo Professor within the Department of Applied Mathematics and ECE at the University of Washington in Seattle. Nathan is also the director of the University of Washington-led AI Institute for Dynamical Systems. He works on a million different things, but is primarily an expert on using machine learning and other data analysis tools to model complex dynamical systems. One fun fact that Nathan offered is that last year, he worked at McLaren F1 on developing machine learning for fluid flows. So definitely ask him about that later. But today, he's going to tell us about shallow recurrent decoders for scientific discovery. Whenever you're ready, Nate.
Great, thank you. Thank you all for coming. So yeah, we're gonna go shredding today. It's like the only thing I work on these days is shred, and and hopefully you'll see why. I'm just really excited about this architecture, which is pretty simple. It's not like I came up with something like, wow, this is extraordinary new design. It's like, okay, this is like maybe what you would teach in an undergrad course, but it's kind of surprising that the pieces weren't put together. And it's related to a lot of theory ideas. And one of the reasons I'll advocate why it works so well is because it's got very nice underlying principles to it. And at least my particular objective is to go after scientific discovery, engineering, real applications that we want to go after with neural networks, and in some sense have some shred of interpretability left over. Okay, all right. I'll try to cut those out. Get them all out in the first slide. Okay. All right, so we're going to start here. Einstein, 1916. He laid down really something very important for us, which was this idea of this physics models sort of should be equivalent regardless of, in some sense, the basis or the coordinates of representation. And you would just have to maybe switch out your dynamical models. But the idea is whatever we're modeling, you should have multiple equivalent representations for this. And in some sense, we think about that as obvious, but in some sense, really, 1916, he's formulating it as a tenet of how we think about physics models. Now, I want to come to this because when we come into machine learning architectures, the machine learning itself is going to sort of be learning models and coordinates for us. And the fact is, if you train a machine learning model, a neural network, if you just retrain it and retrain it and retrain it, all these models can be quite different and still perform all equivalently the same. So the question is, for us, for physics models, we typically would like the model, if we can get it. In other words, something that's more robust and it holds up time and time again versus, oh, that's just the model I got on that training run, right? And so I want to give an example of this. It's very concrete. Maybe some of you guys have seen this one before from me, but just to lay down the foundations, if you haven't seen this, here's what I'm talking about. Let's go to a physics model. Night sky, Saturn, retrograde motion of Saturn, retrograde motion of Mars. This is the oldest physics problem in the book. We certainly have evidence of people tracking planetary motion even before we have writing, right? Written record. So we know that people were very interested in this, and people tracked this, and people wanted to predict the motion of the planets. Okay. The first model of this, there's two things that you need in all of this. So you need a coordinate system or a set of variables to work with. Coordinates and observables or variables are kind of like, in some sense, the same thing. And then within that coordinate system, you need a representation of the dynamics. The first model of this came out of Alexandria, Egypt, 150 AD. So model one is the Earth-centric coordinate system. Earth at the center. Planetary motion can be thought of as circles on circles. All you need is one mathematical thing, geometry, right? And you just need circles. Within that architecture, you could talk about this retrograde motion in terms of the planets moving around on progressively smaller circles. Okay? And this is actually an exceptionally good model. It's linear, it's easy. It's the first Fourier transform, right? The way we should think about it. So Fourier would formalize a Fourier transform much, much later, but this is it right there. And so from an architecture point of view of machine learning, I already have it there, is the idea is to take in the input data, and maybe I don't know what the right coordinates are. I don't know how to represent the physics, but The encoder flips me into a latent space, that latent space being this geometry, this representation, where now the time dynamics is just the behavior of those circles on circles. And then I have the decoder to bring me back out to the original. This is just one model. There's a second model. By the way, I think this is the Roman Empire of theories. 1,500 years before it came down. Okay? And it was replaced, and it's such a simple replacement in many ways, right? It's not like this staggeringly new. It's just like, what if the sun was the center of the coordinate system? By the way, this was proposed in 300 AD by a guy from Samos, Aristotle. Okay, I can't say his name. He's a Greek guy. Okay. But of course, we moved to the Ptolemaic system because he didn't actually have a model for a generative model for the dynamics, whereas Ptolemy did. But here's the coordinate change. Heliocentric, and then within this system, F equals ma with inverse square law. So again, how do you encode it into this coordinate system where then now you represent the dynamics here? Notice it's kind of a separation of variables argument. That's going to be the fundamental driving force of this, is I'm separating the coordinates from then the time evolution itself. Okay. Now we've advanced the mathematics needed. We have to have calculus, relationship among derivatives. And in many ways, we think of this as the right model, right? We think of this as the truth. But both these mathematical models are equivalently accurate. And clearly, they're both wrong, right? So this is a good crowd to talk to. Actually, today I've talked at massively different scales to people. We're talking this level, and we talked all the way down to particle physics. So like the whole range of everything we've known in human history, I've talked to about timescales today. But we're here, so clearly, just either of these are just approximations, but they're very good ones for us and easy for a machine model to train. So we're going to take this idea, but also, why do I want a model in there in the first place that let's say that is interpretable? And there's also a big difference between let's say what Galileo was doing, Kepler was doing and what Newton was doing. And this is like an 87-year gap. We shouldn't, Kepler was the most important person for really getting this coordinate shift done. He was the mathematician that had the ability to do it, and he did it. He nailed it all down in terms of, these are the ellipses. Tycho Brahe had to die. Whatever, however you say his name. Tycho had to die so that he could get the data. Tycho was not an open source person, okay? And his family fought for the data even after his death. But once he had that data, 11 years later, he has his elliptic orbits worked out. You kind of wonder if Kepler would have had any one of your laptops and a Jupyter notebook. Is this like an afternoon of work? Oh, look, ellipses. He could have saved 11 years of his life, okay? But when you're doing all this calculation with pen and quill, a little longer, okay? But interesting, this is an interpolation exercise. And I think this is where I want to move to over here, which is the big difference with Newton. Newton wrote down F equals ma. The solutions are what? Ellipses, the same ones that Kepler already had. But we always think of Newton as the better scientist. And the reason is F equals ma. What can you do with F equals ma? You can launch somebody to the moon and bring them back, for instance. It's a model that allows you to extrapolate to somewhere where you've never collected data. Did we actually believe that model? I'd say we didn't. That's why we launched a monkey into space, just to see, is it the same physics? Because if it isn't, we have to make changes. But it was. Then we put somebody up on the moon. Okay? I want to work in this space. I want to do this. We often talk in machine learning about generalization. I hate that word. And the reason I hate it, it's not specific enough. Because when someone says the model generalizes well, I think what they're saying is it interpolates well. Okay? Extrapolation's way harder. Very difficult to do. And in some sense, our best shot at it so far historically has been if we can write down governing equations. Okay? That's how we've engineered things. This is how we built your life partner. Right? We built this from E&M and quantum. Decades and decades, and boom, here we have it. Your friend, your partner. Okay, anyway, you can dig into that comment as much as you want. So here's what I want to talk about. Let's get to shred, because shred is going to sort of go after these concepts that are basic in many ways, which is I want to go from measurement to a model. And in fact, shred's going to do sensing, model reduction, model discovery, all sort of in one platform. So here's the basic idea. I'm going to listen or measure a spatial-temporal system. Here's just an example of this. And these are my sensor locations. So very few sensor locations. I have 3 of them. I'm going to put them into a time sequence pipe. Could be an LSTM, GRU, RNNs, whatever you want to do here. The latent space of this is going to decode back to that high-dimensional state space. So this is basically a way of doing a generalization of time and space separation. Okay, and space here is more broadly thought of as state variables. Okay, so very simple architecture built out of 2 pieces that are very standard. Surprisingly, we hadn't seen this in the literature. Like, just put these 2 together for spatial temporal systems. It seems so obvious. The fact that we did it seems ridiculous, frankly. Should have been done 20 years ago. But there you are. We put it together. And one of the things that's really important here is normally what I've done in my talks as of a year ago or a year and a half ago, I would said, oh, you should encode and decode. You should take your data, you collect it. In fact, I showed this picture for those 2 models. Find a latent space, come back out. The really big advantage here, the decoding only strategy, there's no inversion to compute. So for those of you who do scientific computing, okay, and I'm looking at the age range in the here, and so there was a software package called MATLAB. If you go out, well, whichever way, go to Natick, right around there, they have the, anyway, MATLAB is a great scientific computing tool, but if you say inf-A in MATLAB, it'll give you an answer and it'll give you a warning, say, please don't do this. Right? We've known since the 60s, you don't compute matrix inverses. It's a dumb idea. It's a highly unstable process. Just a little bit of noise gives you very big answer differences. When you do an encoder-decoder, you are forcing your machine learning to create an inverse pair. You never got around this issue. And what I'm going to show you is some of the results here. I've done these before with encoder-decoder pairs, and it took 6 to 9 months of hyperparameter tuning to make work. What I'm going to show you now, 1 afternoon, because there's no hyperparameter tuning. And the reason I think it's happening, and by the way, I can't back it up. Sorry if you expect me to like write a proof down. I can't. We're trying to work on that. It's just an observation that seems so obvious after the fact, is that don't do an inverse if you don't have to. Decode only. You don't need to do it. Just let the latent space here and this work together without doing an inverse, and it works amazingly well. Okay, so here's the real motivation of this. I talked about this as a generalization of separation of variables. Some of you have had a PDE course, and if you haven't, let me walk you through what it's about. Okay, when I was 20 years old, I went to my first PDE class. Okay, and in that class, that was a class that made me decide I'm going to be an applied mathematician for the rest of my life. Okay, because I love this stuff. But here's what we did on the first day. We wrote down some PDE, and the PDE actually, here's just a more abstract representation. There's a linear operator there. But I consider the heat equation, UT equals UXX. Simplest thing to start with. And here's what we did. The first thing we did is, how would we solve such a thing? Well, separate it into a product of space and time. This is such simple work. You just say, put that in, you get 2 ODEs. And by the way, the requirement for the PD class was ODEs. So you're back in business now. The first one's super easy. It's just exponential, and then you solve a boundary value problem here. And then once you have that, and the boundary value problem gives you eigenfunctions and eigenvalues, and there is your solution. As simple as that. We're only 30 minutes into the class when we get to this. Okay, first day of the PD class. The only thing left here is to figure out these coefficients A of n. Okay, so you have your time, space piece glued together. Coefficients have to be known. So the final part of the class was to say, how do we get the V of n's? We do what's called the initial boundary value problem. To get the A of n's, you basically say at time t equals 0 or something like that, you have an initial condition. So let's call it u0, beginning time. And then once you have that, you can actually project, do an inner product with all your eigenfunctions, and you can compute your A of n. Unique solution. So from all possible solutions to the unique solution. Now think about how fake this is. What physical system could you say, at this time, I have information everywhere, known? We typically make it up, right? And we forward solve. Let me show you a much more reasonable thing, which is calling this the sensory boundary value problem. Here's what's kind of surprising. So I've been a professor at UW now for too long, probably, right? But a long time. And I teach PD classes. I have a whole stack of PD ebooks. And this is staggering to me, this isn't in them. But I could, because this piece is on every single book. And that's where it stops. But what if I instead do this sensor boundary value problem, which is at one location, I have a history of time measurements. Let's say n of them. So system here, I have a that for each measurement location, there's a constraint. I get an n by n system of equations for the event. Unique solution. Think about how much more realistic this is. It is much more likely you could take one location and have a time history of measurements at that sensor than you know the whole state of the system at one time point. Same solution. That's what this shred is relying on. I'm going to trade out information across the whole space to trajectory. That's kind of the mathematical basis of it. Okay, there's the representation. And so this is going to be the architecture. We're going to do it. We're going to generalize that separation of variables idea into time and space, because that's what I did in that first day of class. Okay, so the time pipe, space pipe. I'm going to come in with some sensor measurements. Okay. In fact, what you're seeing here is isotropic turbulence. I'm going to take some time series measurements of that. I can sense anywhere I want. I'm agnostic to the sensor placement. Here's what the sensors look like. And this is work that Jan did here. And then from the latent space, which kind of looks like this, I'm going to decode out here. And it turns out this does an amazing job, even for something like isotropic turbulence, which is very hard to represent in general. Normally in my talks in the past, I do something much simpler here because I can't actually do isotropic turbulence. But with this, no problem. Just train this thing. You need your training data set, right? You need the full spatial temporal fields over snapshots, but now you can say, listen to any 3 locations and go. And the reason you need 3 locations for this 2-dimensional slices of fluid is very much why you need 3 cell phone towers to know where you are. You need to be able to uniquely identify where you are. You need 3 cell phone towers to do that. Same thing here, and you get it. And I can place them randomly. So here's what we're really leveraging, and I'm going to show you the results of this. First, separation of variables. I already showed you that's like a generic solution technique for these spatial temporal systems. We did the decoding only, which I've already made the argument that that's a really good idea, so you don't build an inverse pair. The last thing I want to highlight here is what's called Tauchin's embedding theorem. So Tauchin's embedding theorem is from 1981. It was sort of this cool little dynamical systems trick. It's like really a mathematician's dream. Look at this interesting thing that has no use, right? There's plenty of those. The beauty of it is that sometimes they actually become useful. You don't know that. Many of them don't, but sometimes they magically appear to be like, whoa, that's actually super useful. But Tauchin's has been sitting there for a long time. And here's what Tauchin says. If I have an n-dimensional system coupled together, if I listen to one of those variables, and I time delay embed that variable, that time delay embedding is diffeomorphic to the whole system. So that means if I have a bunch of fields coupled together, I can listen to one of them, and the time delay embedding tells me about what's happening with the others. Guarantee. The problem is it's diffeomorphic. In other words, it's some representation. It doesn't tell me what those are doing. This is where the training data set comes in. But wait a minute, I have a training data set to make that diffeomorphism now 1-to-1. So once I have the time delay embedding, I can say, and I have the training data, I can basically line these up and get that mapped. So these are the 3 ingredients. This is equivalent to butter, flour, sugar. We got a cookie. Okay? Those are the 3 ingredients for all cookies. Okay? I mean, I know they make gluten-free ones, but come on, that's not a cookie. Apologies to gluten-free people. We could just call it something else. Call it a fluky. You know, no, you have to take out the F. This F is for flour. Okay. Anyway, so let me show you how this works. Here's my tail. We're going to start using this to build reduced order models. We're going to build up to learning physics out of videos. So here's some data. I've colored it out for now. What I'm going to do is I'm going to pick, so this is from a benchmark data set. This fairly complex flow around the globe. And we're going to listen to 3 sensor locations on that globe, randomly picked. Okay? Hawkins does not care which one of those variables you listen to. It's not like you have to go searching around like, oh, this place is better than this one. If they're in dynamic relationship to each other, any 3. Okay? I'm going to throw them through a pipe, our LSTM, and I'm going to decode it back out to the full state space. Okay? So that's the architecture. Now, of course, one of the things you see right away is normally when we train neural nets, we have to worry about training time, GPUs, things of this nature. So let me tell you about Christmas morning, 2023. It's me and my dog downstairs at 7. My wife and my 2 girls who are now, and they're like 19 and 22 now. So they don't have any they don't feel any pressure to get up in the morning, right? Even it's Christmas morning, that, you know, when they were little, they'd run downstairs, but now they're like, are sleeping until 9 or 10. So I'm down there with the dog by myself. And so I was like, okay, well, I don't know, I got this new data set that I just gotten the day before. And I have to do this in quiet, right? Because my wife can't find me down there, else I'm in trouble working. So I get this new data set. It was a plasma data set, 14 coupled PDE fields. And I'm like, this is awesome. This is what I've been asking these guys to do. They finally got it to me. But each field was 5 gigs. And I'm like, oh, this is huge. Like, I'm going to actually myself personally have to learn how to use my GPUs. Because usually it's just my students, right? I do laptop level, and right? You can see that's not going to happen before people get up. Okay. So then I said, well, how about if I just take the data at 5 gigs, I'll do a randomized SVD. Because randomized SVD works amazing at scale. 20 seconds per field. Get them down. Okay, I'm in business. 20 seconds, 14 field, that's only like, so, you know, within 10 minutes of just writing, boom, I got all the fields compressed. And so now what I'm going to do is not do this, but I'm going to go ahead and say, take the data, compress it. Don't train on the full high dimensional state space, train on the compressive version. Super small now. It only took me 20 seconds to get this for each of the fields. Now you do this. You train on the compressive field. By the way, I'm training here, and now I'm training in minutes on my laptop. So Christmas morning, 2023, compress the fields, train this model in 5 minutes, take the dog for the walk, come back, everybody's still asleep. And I already had my Christmas. Good, it totally worked. All right, so then we go. That's a nice Christmas gift, right? To oneself. Usually doesn't work out that well. This Christmas it did. All right, so that's the idea here. And then you can also say, well, wait a minute. One of the big deals with model reduction is how do you handle parametric variation? So we can, well, first let me show you the result of this. So what you're seeing here, 3 sensor measurements. Again, here's the ground truth. Here's the reconstruction. Here's the velocity trajectory. Here's the reconstruction. And here's the difference. And you can see with 3 sensors, you really do quite a nice job of being able to do this. And so now what you really have is this really nice representation of this very expensive simulation that was come from the well, now down to this simple seconds level compute that I can generate this stuff with. Another thing you can do with this is you can actually have a mobile sensor. Do you see the little, I don't know if you can see it, there's a purple little dot moving across there. One single mobile sensor, as long as you know its location and take the measurements on its trajectory, allows you to do that reconstruction. Okay? You can also say, well, that SVD, but look, it's a sphere. Spherical harmonics are a great generalized basis for this. So instead, compress it onto the spherical harmonics, and that's this here. So all these kind of work. Yeah. Yeah, no, so limits here are, so for I have to have the good, if I have a training data set, right, so the unreality of this is that I have to have the training data set, which is I have to have some version of this at some point. But once I have that, this is essentially a 2D surface, right? It's because all the dynamics are on the sphere. I can get down to any 3 measurements there, and I can just train this thing. And all of a sudden I say, if I just listen to these 3 locations and I tell you what's going on at these locations, I map it out to the full state space that's there. And of course, just like anything else, depends upon your training data you give it, right? So whatever it's sampled, it can reconstruct those behaviors. So if I go through a bifurcation, it doesn't work. It's not in the training data set. However, towards this goal, we went and did this, which was, yeah, but this is the problem. My system can change over time or have different parameterization. So we said, let's take this model and train it across parameters. So mu1 is a vector of the parameters, and I just train it across different simulations with different parameterizations. And what I do is I jointly SVD all of that data and put them all in, chain in a compressive fashion, boom. So I've got myself input-output pipe parameterized by some parameter. In this case, it could be geometry parameters, it can be flow characteristics. I'll show you some of that. So I train that all offline. And then online, now I go and deploy this and say, just listen to the sensors. I can go to a new parameter regime. And in that new parameter regime, just turn on my sensors, throw the sensor measurements in, and I'll tell you, and here's what the flow is doing. So that's the nice thing about a reduced model now, is once you've trained across parameter regimes, I can just go to something new and listen.
So I've got a question for
Yeah.
So I've got a question about, I could imagine that there are multiple configurations that have identical instantaneous signals on your 3 sensors. But what might differentiate it is sort of what happened before, so like the time.
Yes.
So it would seem that, do you need some sort of, like if I don't tell you about anything that's happened before and I tell you to predict, it seems like it's probably not going to be one-to-one mapping because it's using the time information to differentiate between degenerate values. So is there like a warm-up period for?
Yes, in fact, there has to be a burn-in. So like if you start this thing, in fact, we trained it with a burn-in. So when we did the training, we said, okay, at time 0 when the data starts, we'll just say all the recordings up to that point are 0 on the sensors and then start training from there. It actually works surprisingly well even with that, because then it's just a decoder network, and those are actually quite powerful, but this is even one level above that. Yeah.
And when you do something one shot without time history, is it giving you a possible reconstruction, or is it averaging over possible reconstructions?
Yeah, it's giving you one realization that, I mean, you still get something that looks right, and sometimes it's actually pretty close to being right, but the time history massively constrains the inversion. That's the main thing that it's actually doing for you, is to do that. But we wrote a paper in just shallow decoding, and that's actually quite accurate, even that by itself.
Is there an explicit sampling procedure that allows you to choose a possible? Because otherwise, it's not obvious to me that it would pick one.
Sampling of time or space?
Let's say I just give a single time sample on the 3 different sensors, that it would give me one possible outcome without a sampling process.
No, the sampling is just on a clock. I just say whatever delta t is, whatever the training was, boom, doesn't care. Pretty agnostic to it. There could be ways to improve it, but the performance here is so good that, like, as you'll see on some of this, that we just put on a very simple sampling clock without any magic to it. But that's how you would do a parametric version of it, or is there another? Yes.
Also, won't the map change based on the three points you're choosing? So like during training, are you choosing like.
Yeah, so if
different
you're when
combinations?
you train, if you fix your sensors, training and test have to all be on those three sensors.
But
But
could
with the moving sensor, it's a little bit different because you can, if you have it moving a long training data set with, as long as it's set, okay, tell me where your sensor is and here's what's happening over time in that sensor, it can actually do a much broader range of reconstructions.
But for these results, are you just training it on 3 fixed sensors, or are you also like
Yeah.
encoding the position of the sensors?
No,
and
just
trying
3
to-
fixed sensors. Yeah, because there we're not moving them, so we don't have to encode the position.
But do you think you could, if at training time you change the position of the sensors, but you also have some way to like encode the position and pass that into the
You
network?
could, yeah. Encoding the position over is easy. Right, and that's what we do with the moving sensors. In fact, it actually kind of improves it a little bit. Here we just fixed the sensors to 3 and there's no problem. In fact, what we did with this is a lot of this was trained on things like, then we went to like real video. So for me personally, I've done a lot of applied math type methods, whatever, and we typically do it on model systems. But now this also allows me to do model systems that are much more complex. Like here again is video from these, benchmark data sets. And that's the original video. And here's the processed video. Now that we take it from RGB, map it out to grayscales. And then those are your 3 sensors. Here's your reconstruction. And by the way, this isn't a parametric. This data is parametrically varying. So this is the new parameter regime, what you're seeing here. So this is a test set with a new parameter regime that we didn't train on. That's the reconstruction. And this is for some asymmetric flow. It has an alternating pattern here. Same thing. So, and again, I'll emphasize that the training time here is minutes on a laptop. Nobody needs a GPU. Okay? So those are the kind of things that are really nice for model reduction, because now you're off of this. We can also do something else that has been, I think, a really tough spot for machine learning, which is shape, geometry optimization. How do we handle that in neural nets? Now, you can clearly build a graphical neural net, but these are almost as expensive and as big as just doing a forward solve. Because the mesh you have to have, the graph, is so massive. You just say, well, that's as big as my finite element mesh, so just run the forward model. But here what you're doing is we're changing a couple of the geometrical parameters, which is the shape of this and angle, and 2 physical parameters. And so we are able to, again, train this and start doing shape optimization with this. So you're seeing there the velocity trajectories and the reconstruction. And in here is sort of the data. I think this movie isn't working. Sorry about that. But here are some different algorithms that people commonly use right now with physics-informed type neural nets or operator learning. And there they are. But like this just not only does it do better, it's like training time is orders of magnitude less. The amount of data you need is much less. The model size is much less. You kind of win in all the metrics you want for machine learning. And why? Because we're just using those 3 concepts. Separation variables, tokens embedding, no inversion. Many of these have inversions, and that's already costing you a bit right there. So here are some performance metrics. And then so I wanted to show you here's the Christmas morning story. I'll just show you some applications of this. So this is the data I had. It was from a Hall thruster, from a plasma. This is one of the 14 fields. This is the reconstruction of that field. I'm not even measuring this field. I'm measuring a different field. And what you're looking at here is the construction of this is one of the velocity fields. And I'm measuring the temperature, I think. Okay? Here's another example. This is a nuclear reactor. It's 21 coupled PDEs. This is a very high dimensional system, HPC. What you're looking at is the full order model. This is really expensive to simulate. And this is essentially the shred proxy. And what we're doing is we can construct all 21 fields just by measuring the temperature on the walls of that thing, which is the realistic thing that you would actually be able to have access to. All those fields are coupled together, which means the time delay embedding of the temperature field has information about them. And with the training set, we go from the diffeomorphism to 1-to-1, and you get this nice reconstruction there. We also applied this to geophysics data. This is a group out of the University of Washington. where you see all those red dots. These are this massive sensor network that they have up around Alaska, measuring activity, geophysical activity. And we basically said, oh, you can replace all those and just replace it with, they have this new fiber cable in there, and they just say like, yeah, you can just train it all the fiber cable. So the fiber cable alone can tell you what's going on across that whole geographic regime. Tells you what's happening on all those sensors. You can see the cost savings of this. There's very much in the sensor community this idea of more sensors, more sensors, more sensors, more sensors. And this is saying, actually, obviously we have to have a training data set. Don't get me wrong. That's going to initially require more sensors. But once you have that, then you say, oh, now I can back away and just listen to 3. And I got this. All right, I'm going to skip that. Okay, so where do we want to go with this? So now this gets to what I really want to talk about. Yes?
Sorry, just one more question on kind of that point. Is there any sort of statement you can make about like how high res of of sampling you need for the initial fitting to then go down to your 3 samples? Because I could imagine like if you have a more sparse sampling of your field, maybe it won't quite be 1-to-1 on your...
Space or time? So as far as we have, so I did this with, you heard here, I was at McLaren F1, right? I plopped this onto some of their things because if they really want to figure out, can you measure pressure on the car? Can you figure out the flow physics? I told me you could totally do that. In fact, why don't you give me any 3 pressure measurements you want on the car? You can't do that. There's no way you can do that. Just humor me. Send me the data. So I made a movie for them, and I sweep through any 3 pairs. It doesn't matter. Like you can have 2 sensors on top of each other. There's obviously edge cases where but with high probability, you pick any 3, anywhere, any spacing, as long as the dynamics are coupled. You can't have a region that's statistically independent, but as long as they're coupled, it works.
Yeah, so the question is not on the 3 you select down to. It's how high fidelity does your initial data need to be to fit?
Oh, so, well, whatever, it trains to whatever fidelity data you gave it, right? So if you gave it a fairly coarse grid, you'll get back the coarse. If you give it a very pretty fine grid, you'll get back to that. But neural networks always do some signal processing. They do bandpass filtering. Yeah. So you get a little bit of shaving of high frequency content in space and high frequency content in time, both. But compressive training actually preserves a lot of the high spatial frequencies because when you do the SVD, it's saved and the neural network doesn't trim it off. Yeah.
How important is that the sensors are localized at single points as opposed to, for
example,
even if the simulation is high fidelity,
yeah,
my sensor is kind of averaged over a bigger patch?
You can do that too. Yeah, you can do patches. You can do random projections. There's lots of options here. Mostly what you need, though, is 3 independent measurements of some sort. But here's what we want to do. I left some money on the table. What I mean by that is I want to do GoPro physics. So here's the idea of GoPro physics. And I think, film something. Yes. Oh,
I just had a question.
Yeah.
So you said the sensors need to be independent of
No.
Did you?
Just 3 sensors anywhere.
I see.
Anywhere you want. I can't, though, measure here, and if there's a statistically independent regime, believe I could model that, right? At some point, right, like, oh, I'm measuring this body of water. All my sensors are here, and there's a body of water there completely disconnected. That's hard for you to do. You can't do that.
So there is no idea of optimal sensor array placement?
No. I spent 15 years working on optimal sensor placement. 15 years. So when I say you don't need to do that, I'm cutting down myself. So it's not like I'm telling you, those guys don't listen to them. Those guys is me saying, oh, here's how you should do optimal sensor placement. Now I realize that you don't need to do that at all.
And what if you have a lot of sensor noise?
This seems to be very robust to it. I'm going to show you some videos now because we're going to go straight from videos. And there's a lot of this I can't like back up. So, right, like, let's be honest here, right? I'm just going to show you this stuff, show you the results. And like a lot of neural nets, it's like, look at that. I made some statement about that in verse. I can't back it up yet. I'm hoping one day I can. But here, I'll show you how well it works in real data. And you saw some of the real data, real videos of the flow physics, right? And that's always, to me, the metric of success. In fact, how I knew this was special, this method, was when I did it on some of the F1 data, because that is real data and it's terrible signal to noise. I mean, really awful. And it just worked. It just boom. And that's when I knew, like, okay, this is magical, because normally stuff like this would take me months and months of, okay, I got to process it all, do this. Here's the 10 tricks I got to do to make it work. I did 0 tricks, worked first time. So that's not a that's not a theorem, obviously, but it's just an observation for you. Yeah. Yeah.
If this is some sort of a system identification, right? Can we call this a form of system identification?
I'll show you this now. This is going to be it.
Because in traditional system identification, you need to excite the system at different frequencies, and then you sort of try to reconstruct. But your reconstruction accuracy depends on how much, like, how coherent your sensor was and that kind of stuff. So when you don't have such metrics, like how confident could we be that, from just the sensor measurement we are reconstructing the actual physics, where there could be issues like it was not coherent or it was noisy and it was correlated.
Yeah,
kind of
I don't know if I have a good answer to that, except for I'm going to give you the computer science answer. I cross-validated across a lot of data, which is not a satisfactory answer, I know, because I'm in applied math, right? But that's the best one I have for you right now. But let me walk further down to this thing, which is I want to now do this, which is we've already talked about going from video, and I want to do GoPro physics, which is I want to just film something, and I want it to tell me, like, oh, here's your governing equations. Here's a model for this. It's very nice to represent. So let's go back to the same architecture, same as before. And this is now with Mars. And same architecture, we traded out the LSTM to grooves. And now what we do is we left one thing on the table, which is we said, hey, we didn't do anything to that late space. And now what we're going to do is go down to that late space, and we're going to impose some restrictions on the late space. We're going to say, in the late space, give me a nice model. What do I mean by a nice model? Well, here, we're going to put in what's called SIND or DMD. So for those of you who are not familiar with SIND or DMD, let me show what they are. Here's what SIND is. SIND is a way that if I give you time series data, for you to tell me what was the dynamical system that produced that time series data. Okay? It's a very simple architecture. It's AX equal to B. So the idea is I give you some time series data of X, and it comes from X dot equals F of X. You don't know what F of X is. But I gave you X. I took the measurements. I gave you X, which means you can compute X dot. So in the X dot equals F of X, you have the left-hand side. So that's the B in AX equal to B. What is F of X? Now, you don't know. But what we do with Cindy is say, let me give you a library of possibilities. Where do I get them? From the library, right? You can pick up all your books and write down models. We have lots of physics models. You say each one of the rows of that matrix is a candidate term for what could be the F of X. That's the matrix A. So AX equal to B. What's X? And this is where the magic comes. It's just a simple AX equal to B solve, except for now what we do is say the big leap here that we typically do in physics is parsimony. Maxwell's equations fits on a t-shirt. Quantum mechanics is 3 terms. Navier-Stokes, 3 terms. If you look at the history of our physics modeling, we could often write down something very compact as a representation of the dominant balance physics. So out of all these candidates, I want to select as few of them as possible. So promote this idea of sparsity. So X, B, sparsity, boom. So in other words, if I give you that data set, it brings you back and says, and here's your dynamical system that produced it. So that's the regression framework. It's very simple, but we're going to make that happen in the latent space. Okay? Or we could just do a linear model. And linear models, if you do regressions to linear models, dynamic mode decomposition does this, which is just fit it to a linear model. What does that mean? Well, that's the solution to the linear model, exponentials. In fact, that was a separation of variables solution that I wrote down earlier for a linear system. So you say, fit it to the model. That's it. There's like no training here. It's just a direct fit. And by the way, both Cindy has a package, PyCindy. You could pip install it. and PyDMD, install that too. These are nice packages, mature, you can do examples from it. And so we're going to just take these and put it in that latent space. So we're going to say, in that latent space, enforce a Cindy model. Find me a governing equation for now the latent space trajectory. And in fact, what you're looking at here is the actual data we put in there, which is sea surface temperature data. So this is real data, 20 years, downloaded from NOAA. Weekly sea surface temperature data fluctuations. We pinch the latent space as far down as we can. In fact, we can pinch it all the way down to 3. There's the dynamics in that latent space with 3, and that's the model. So the dominant physics in that sea surface temperature data is that 3 by 3 linear ODE, which, if you took ODEs, it's like a homework set. It's that simple, right? Just work it out. You find its eigenvalues, you find its eigenvectors, you write down the solution, get 100%. Right? Undergrads can do this. Okay? And that's the latent space. Z1 is attached to this mode. Z2 is attached to this mode. Z3 is attached to these modes. These are the modes learned in the decoder, and they are nonlinearly combined to reproduce the dynamics. So now you can do like these rollouts into the future. There's the real data. Here's a 100-week rollout. That 100-week rollout is me writing down the exact solution 100 weeks in the future. I'm not even doing computation at this point. Just saying, here's the solution, glue it back to the decoder. And you can see you get most of the, right? High frequency stuff gets filtered. And I think what we need to do here is, I think we're working on a multi-resolution version of this where we refine different time scales, because there's a daily time scale and we kind of on a weekly clock. So it's hard for us to resolve the faster scales. Okay, yes.
I guess these are chaotic systems, right?
Yep.
So, which are sensitive to initial conditions. So how confident can we be that, like, 100 weeks? So is your method also sensitive to chaos?
Yeah, you can do a probabilistic forecast by taking a little Gaussian ball and watching it spread. So essentially what you get is a little bit of like the Lyapunov time type architecture that's there for the chaotic system. So it's a one more bit. Oh, here it is. Yes. The great thing about the internet is YouTube, right? Look, there's a YouTube video that I couldn't have built this, or like someone would have put a lot of time into it, but someone did, and they put it up on YouTube. Love YouTube this way sometimes. I don't like the infinite scroll because I get caught in infinite scroll mode. But this is from the internet, and I say, okay, what is this physics? I'm going to do the same thing. Put some pixel. Of course, you can't listen to that corner. There's nothing happening. Remember, you got to put something in the causal window, right? There's some practicalities. But you do this, and check this out. There was the original video. Turned it into grayscale. That's here, the real data. By the way, it's original video. This is, we trained on 200 snapshots. Now we're running it out 180 frames. So very little training data. That's the real data. This is our prediction. This is the model it finds. 4 by 4 nonlinear ODE that has a fixed point with a limit cycle attractor. If you don't like a nonlinear model, make it be a linear model. Now it's a 6 by 6 linear. Now, the difficulty with a linear model is, actually, it's a great fit, but this can't go through a bifurcation, where this one here, you can now say, oh, what happens to this as I start changing parameters? I can now start making predictions of like, I think if I go up with this parameter, somehow there's going to be a bifurcation, which is exactly what happens in the system. You keep going up. And it's going to predict for you that there's going to be a change in the dynamics, right? From real video, afternoon level. When we've tried to do real videos before, it is a sad fact that it has been a 9-month process for us, hyperparameter tune. Of course, we don't tell you that. We say, look at this great result, right? You guys as grad students, those of you who are trained that 9 months, you like keep quiet about it too. You just say, yeah, I'm awesome. You don't talk about how many times you might have cried trying it. You just suck it up, and then you got a good result, and you're happy it's done. But that has been our storyline. And this is why I'm so excited about this, and why I keep just working on this method because you see stuff like this and it's like, wow, and it's afternoon. Oh, by the way, all this code's available to you. All the data is available. You can run these codes right now. Okay? I told you it was laptop level computing. It's not like, say, you can run my code. Do you have 1,000 GPUs? Right? I've seen this at a conference before. Like, guy up there, I'm like, what a terrible move. Oh, yeah, code's available for free. You can just download it here. I don't know, take out 2 months and 120 GPUs. I'm like, who's got 120 GPUs? And who's got 2 months? Like, it's a stupid statement to say, right? Anyway.
I had a question about the bifurcation.
Yeah.
So how does the bifurcation manifest, like in the forward prediction?
Yeah.
Because again, it seems like you're not doing like a
Yeah,
sampling
so
procedure.
what we can't do is actually model the bifurcation. We might be able to predict that there's going to be an instability here, but this decoder doesn't have the right modes to represent it.
So what does the prediction look like? Does it look like an average or does it?
So the prediction here would be a stability argument where this limit cycle goes unstable. So for instance, as one of the parameters, you might say, here's the prediction. And what you really want to do is say, oh, if I believe that to be true, this is a way of doing what I say, walking out extrapolations. This would say, oh, this means, it's going to be related to that Reynolds number. If I go up to this parameter value, something interesting, let me do the experiment there where I'm predicting interesting things to happen.
Okay, so you would like reinitialize.
Yeah, and then you reinitialize.
And
yeah.
It's clear from something about the system that you would know how to reinitialize.
Yeah, you would know how to, exactly. You know kind of at least where to do your next experiment because your decoder is not generalizable.
Okay.
Unless I trained it on both sides of the bifurcation. Then it would have the spatial structures on both sides. But if I train it in this regime only, it's like any neural network, you cannot extrapolate out those modes.
Okay, and the reason why it's easy to kind of sample at that bifurcation is because like you essentially have coordinates in your dynamical space.
Yeah, that's right.
Okay.
Yeah, yeah. So anyway, these are some example. Here's another one, pendulum, right? Pendulum on a wall. There are many MIT corridors that look like this, right? This is a state school. I love these. Like, I feel like there was an architects convention for universities where they all got together. You know what would look really neat? Is like, how about off-white cinder block walls with off-white linoleum floor with an off-white thing, and then it'd be amazing. And they all agreed it was amazing. And they all built buildings like this. But the nice thing is when you now drill a hole in this, nobody cares. In fact, if anything, it's like, oh, we've put art up on the wall. Okay? So anybody wants to do a pendulum experiment, you got lots of walls, at least on the 6th floor, before you get into your nice space, you could put a pendulum there, right? But you videotape this. Here's your model. Gives you a pretty nice nonlinear pendulum model, straight from the video. And also, we compared it to the leading methods in machine learning, like computer vision is very interested in video prediction of physics phenomena. Here's all the leading methods. Not only do we get a better accuracy score, the training time is orders of magnitude less. The data requirements are much less. The model side is much less. So you're winning across the board. Why? Because we're actually taking into account the physics structure, my view. Okay. Last one here that I want to just show you. This is turbulent flow. Turbulence is really difficult. What you're looking at is the real data up here. Here is a shred prediction of it. And what we did in the latent space is say, can we characterize turbulence some way? And actually what you get out of this is, in the latent space, you have a 20 by 20 linear ODE characterizing that turbulence. So then it goes back to when you roll it out, of course, your Lyapunov time is short, but the characteristics of this, you keep all the same spectral content, like the power distribution of that flow is really well modeled by a linear system. Okay? So what it's telling you is that even something like turbulence, approximately, there is a low dimensional embedding of that. And a simple model. Okay? All right. One last miracle. I know it's MIT. You can't really talk about miracles. You can't believe it. Can you believe in a miracle? If you can, it has to be completely explainable. But let me just, since it's not explainable yet, we're going to call this one a miracle. All these things work kind of surprisingly well, right? Like across the board. And really, literally, all these notebooks are up. You can try them. Laptop level computing, real data. And one of the reasons we also figured out it works so well is the following miracle, which is this one here. This is the loss landscape of the neural network. It is globally convex. Now, anybody who's trained a neural network and has looked at the loss landscape, it is usually a jagged pile of a bunch of local minima, all this stuff. And that's why you need ATOM or SGD to kind of walk you out of all these local minima that are sitting everywhere. Across the board, shred, Cindy shred, across all the examples, what we have found to numerical precision, global convexity. This is why when you download this code, if you choose to, you won't have to do any hyperparameter tuning. You can just run it right out of the box, which is, again, the miracles related to this. Yes?
Do you mind saying like how you're actually plotting the loss or like getting the loss landscape?
So we take the loss landscape and you pick two random vectors in that loss landscape and you do a 2D projection on those. And if you look in the supplemental material, we did a bunch of 2D projections.
Okay,
like we were exhaustively searched random projections in 2 dimensions where we could plot it. Yeah. So there you go. That's it. I think at the end of this, what I would say is this decoding only architecture where you separate time and space works amazingly well. It's so simple. Like this, hopefully in your mind, like surely somebody did something like this. Maybe, I don't know. Seems like such an easy idea. Like it should have been done like one of the first neural network architectures long ago. But now also we're manipulating the latent space to get all this stuff out of it, and it's quite works. So I'll finish here. I apologize, a little self-serving, but I think this is important. If you go to YouTube, you can just type my name, Kutz, shred, or shred and Kutz. No, I don't know if you can do shred Kutz, whatever. You'll find a playlist. And in that playlist gives you overview, a lot of examples, a lot of work code. The students will go through work code. And there's even a PyShred package that we've built out that's super easy to use. It will be available for a pip install probably in another month or so. But you can just clone this right now, and it does all this stuff. So it's just invisible. You just take your data matrix, you do shred.fit. Boom, done. And even the Cindy shred is in there. There's a very nice Colab notebook if you want to walk through, which is the example of the sea surface temperature data. Just simple walkthrough explains everything, where you can just put your data in and walk that through. Part of what we're trying to do is make this as easy as possible for anybody to use. And that should always be your goal as well. If you're writing code, you want people to be able to like clone it and boom, runs out of the box. Super easy to know how it works. Okay? And then with that, I'll stop. Thank you so much.
Nathan, yeah.
Thanks. So this is really fun.
Yeah.
I have a question about the missing high frequency details, right? So you say it's a multi-scale problem, but I'm still confused also by the missing information, right? The inverse problem can't be fully determined by 3 sensors, right? Even if you have a full model. So isn't it a problem of that you need your decoder to be probabilistic and sample the possible configurations rather than a multi-scale problem?
Yeah, so it's a good question. I mean, I don't think you could make a decoder be probabilistic, but the fact is, let me just show you the example here. This is the good example where you can see it. There's a paper written by Benjo's group on essentially the training bias to low frequencies in neural networks. And really what he's saying, he never mentioned this once, but that paper just basically highlights it's a low pass filter. The reason it's a low pass filter is partly because of the root mean square error. The root mean square error is going to focus all of its attention on getting most of it right. The high frequency stuff hardly contributes to your RMSE, and so it just ignores it. So you can see, I don't know how well you can see it from where you're sitting, but you can see, look, you're getting, but if you look carefully here, you see how it got filtered. It's basically a bandpass filter. That's generic for all neural nets. Yeah. Yeah, you could potentially put a diffusion. We've put a UNet transformer on this. We've had lots of architectures. So you could potentially get that multi-scale feature back at this. Yeah, but we haven't worked on that so much. So it all depends on kind of what you really want to go after. The other thing you could do is not instead of RMSE, you could train this and say, actually, I know what the spectral decay should be. I should actually put a loss function, which is RMSE plus, you know what? This should be decaying at k equals -5/3. And then you put it in as part of your loss function directly. Yeah, yeah.
We do have one question on the line. David M., if you want to unmute.
It
David,
almost
are you
seems
there?
like,
Oh, yeah.
hello?
Go. Yep.
It almost seems like you're getting a tremendous amount, quote, for free. I'm wondering, are your three sensors with a time series, are they sort of analogous to a points in phase space? Or is this an analogy? Is there an analogy to holography here?
To a lot. Oh, good question. I don't know if I have a good answer for that one. I don't think I know enough about holography to make any meaningful comment there. The only thing I'll say is that obviously, and I'll say it again, we're not doing anything special, right? We're doing stuff here that's really simple. We know that Tawkins says a time delay embedding tells you about the other variables. And we're just using that without a decoder. And there is a question about, I think, part of phase information, what you're picking up in that. But we haven't, I guess, we've always just, so far, we've just done video. We haven't done something like a phase recovery type problem with this yet. So maybe that would help if we did something like that for me to have an intelligent answer to you. Yeah.
So thank you for your time. So I have a question about so you mentioned three aspects. But first you mentioned, okay, using Tawkins embedding theorem, variability of variable of separability, and then also not using a sort of like encoder in this thing.
Yeah.
But then of course then you're using all right, let's use some sort of technique to have a latent space. You use SVD. Yeah. Is there anything you can tell us about what sort of problems are amenable to for this sort of approach? Because you showed us at the end this sort of landscape, and I say, all right, this is all convex, very nice, very beautiful. What sort of problems are amenable to this? Because you mentioned isotropic turbulence, right? Like if you have suddenly something there that is generating a new sort of thing, even if it's all linked, if it's all linked dynamics, but now you're actually perturbing the system in a different way. Is this still usable, or do you have
Yeah, so I could tell you some directions we're taking it, which is one is this perturbation idea. We're taking this to control ideas, which is instead of just embedding the sensor measurements, you actually embed your actuation signal directly into the latent space, and you build a control model in the latent variables. So z dot equals az plus bu, right? It's either you, your signal, or let's say a neural network warped version of you. But we're moving towards exactly that idea. Now, as far as that landscape goes, every single example I've shown you so far, every single example we've done, whether it would be the nuclear reactor, the plasma physics, the isotropic turbulence, neuroscience applications, measuring neurons to full state space of the full brain imaging, every single one of them has that landscape. It doesn't care. Even if it's an actuated system, if it's an actuated system, it's a little hard to get at. You're hoping that the sensor recording itself has a signal of the actuation, but those are a little harder, right? But we are moving towards doing the actuation itself. So far, we just haven't found we are trying to break it all the time, and it's surprisingly robust and hard to break. And the beauty of it is it's so fast to program. Like it's not like I'm going to try to break it, but every time I try to break it, I'm committed to weeks of computation time. When I try to break it, it's like I'm spending an afternoon trying to break it. So we can really very quickly fix things, but we haven't had to fix a whole lot. Just kind of like very stable architecture for whatever reason. I can't explain it, but I'm just telling you about it, and we're excited to use it. Yeah. There's one here. Yeah.
Thanks for the great talk. Lots of interesting things that I want to ask, but maybe the first one I'll ask is, in a sense, like your results seem to say to me that if I give you enough time horizon on these 3 points, that I can somehow guarantee 100% correlation between those points and every other point in the system. So it seems like, could you kind of go the other way, trying to see like how little of a time, like basically sort of like a correlation length of your system, and also like, just how, also the other side question is, you're talking about like randomized SVD, but then it seems like there's close relationships of like different types of tensor decomposition. I don't know, do you have any comment about, I guess those are two very different things, but so correlation length, kind of measuring that by virtue of the error that you would have by making different choices, and then SVD versus different types of tensor comp.
Yeah, so the good question, first of all, I'll address one thing about correlation length. So clearly there's a time delay run that goes into the LSTM. We've made it fairly short, but you could say, well, I can make it longer. In fact, when we have sensor trajectories that are random and arbitrary, we need much longer trajectory information. But you can't keep going until, because if there's a decorrelation time, and you can't essentially walk yourself into a decorrelated time frame. So you have to keep your sensing time essentially below 1 Lyapunov exponent in the sensing. Now, in most of these cases, we're not even close to the Lyapunov time, so it's fine. So at least we have that advantage. The other question was on tensor. Yeah, so let me tell you where we're going with this now. What's interesting here with the compressive training, I'm working with a group at Barcelona Supercomputing Center. And so we are working on, we're trying to go to scale. So first of all, I don't know if we'll be able to call it this, but I want to call it the Beyonce matrix. Because if those of you who know Beyonce will know that she wrote a song that says, what's better than 1 billionaire? 2, thank you very much. I'm always surprised when people don't know the answer to that. Okay, so get your Beyonce right, but 2 billionaires. So what we want to do is billion by billion matrices. Like you just say, I've got massive flow sims, for instance. And Barcelona Supercomputing does. They actually simulate Barcelona airflow across buildings. It's this massive scale. Then you ask the question, how do you handle that data? Even if you want to partner with them, can I have a sample of your data? Sure, it'll take you 5 months to download, right? Just 3 snapshots. Just huge. So what we're doing instead is we have a pathway to take a billion by billion. You use randomized techniques to handle the fatness of row space, that billion. And then you do a parallel QR to handle the height. This can then just all of a sudden pop this billion by billion matrix down to something that is number of time components. Okay, I got 2,000 time slices, billion, actually I have a billion time slices, but only at 200 dimensions. And then we can actually just write code on that level on your laptop. So it doesn't even matter if it's anything of scale. All these tensor decompositions, big scale decompositions, if you can compress it, right, they all give you a compressed representation. You just train on that. And the only time you actually look to see what it's doing is on the fly. When I need to visualize it, I would pop it back out through the decomposition. So it's a little bit like your phone, right? Your phone, you take the picture, it's saved in compressive fashion. The only time you actually see your picture is it decompresses on the fly to show you, right? So that's what this would be doing. So we think we have a pathway to scale, but not just to scale. It's to scale, but then humans can work with that data. So instead of them trying to say, hey, look, I've got a petabyte of data to share with you, and you have no way, you don't have a big enough computer, even if you don't have a big enough computer to put it on or download it. But they say, look, I took the petabyte and I don't know, I shrunk it all down with this compression to a terabyte. I'll order a drive on Amazon. It'll be here this afternoon. I'll download the 1 terabyte, ship it to you. Or like at that point, you could actually FTP it. And then you're working in this space where you can actually like, actually, I can work with this data set. Not only that, if you want to reproduce it, all you have to have is the map back out to the full state space. So I think it just allows people to work at scale, right? Because I think those are the hard problems now we want to go to is massive scale. And this is at least a pathway we can do that.
I was just curious, say you have 3 sensors and one of them is defective, and say you are doing it at scale, so you don't know which of them.
Yeah.
So will it still be able to how would it work in a scenario where some of
Yeah,
the
yeah.
sensors are defective?
So you still do fine with 2 sensors, not as good as 3. But what we have now, we're building an architecture, we have it almost done, which is instead of 3, let's say 3 is a little bit of a show-off move. Like, I could do this in 3 sensors. But you say 10. And what you do now is you train 3, choose 10, right? You just randomly pick 3 out of the 10. You train a shred model because it takes minutes. Then you take 3 random again, train a shred model. Now you have uncertainty quantification. Because I can say, I'm going to train 20 models with those 10 sensors, 3 randomly picked. They all should agree. So when you ask me to do a forecast or build a model, I now can say, here's the result of the 20 things. Now, if you find one is off, they have to all agree. You might find that, oh, this one seems to be way off. Oh, all of these models that are way off are using this one sensor. So I think there's a way to identify a broken sensor and then eliminate it from your pool and then have uncertainty. Yeah.
Thanks for the talk.
Yeah.
I really enjoyed it. I have another question about sensors. You said you said you didn't really want to talk about optimal sensor placements. And this seems fairly robust, I guess, against sensor placements. But if you could pick where your sensors go, there's probably some notion of like where would you want to measure.
Yeah.
And also you said you can measure different fields. Like it came up when you did the vortex jetting case with the incompressible fluid, like the information can propagate through that entire continuum, right? So you said you can like put a sensor in front of the cylinder, but
because it's like
the same continuum. So like if you measured pressure there, maybe a bit better than measuring velocity there, for example. So could you comment on like how you could pick what you measure and where you measure it using this?
Yeah. So the standard way of doing, let's say, optimized sensor placement for those people who've worked in model reduction would be like, I take SVD of these snapshots and I do QR selection, QR pivot points, or I can do IMs, dimes. There's these optimal selections that are based upon SVD modes. In other words, wherever the variance is largest, put a sensor there. So that's the standard way to do it. And what we found is it doesn't matter. You could do that. In fact, we've done this where we've said, let's use these optimal sensor frameworks in this. And it's like, yeah, pretty same performance.
So that just means you have very like robust technique.
Yeah. But and again, but like if you look at the movie, nothing's happening here. So obviously, you have to have the sensors be a participant in the physics. That's one.
Right.
And be coupled to the other variables.
For something much more challenging, like with the globe prediction, there must be like some better spots to measure, no?
Well, all I can tell you is what we've done. Like you do 100 trials, each trial you say pick 3 random, pick 3 random, pick 3 random, and then you just plot the mean and variance, and it's like really tight variance around some mean. In fact, I think I showed a picture of this. So that's I can't remember if this is different. I think this maybe okay. I'm not sure if this is different sensor. No, these are fixed sensors, but you kind of get things like this where you just pretty crushed down mean, even if you just do random versus the ideal. They're kind of like there's a little bit of variance, but not much. Yeah.
That's quite impressive.
Yeah.
Super
Yeah.
realistic.
Yeah.
Okay, let's thank our speaker again.
Thank you, guys.